Today we're going to talk about the history of how we have determined the structure of the atom. As a little preview, we're going to talk about the three particles that make up the structure of an atom, and I'm sure you've heard of them before. Those are protons, neutrons, and electrons. We did not always know about these particles, nor are we going to get into what we now know about those particles is that they are also made of particles. We're not getting into that today, but we are going to talk about how we got to the point that we know that atoms are made of protons, neutrons, and electrons. This all started a long, long time ago. In fact, in about 1803, a gentleman named John Dalton came up with a theory that atoms were very, very small and they were indivisible, meaning that you couldn't break them into smaller pieces, and that they were solid particles. We call this model of the atom the cannonball model. This was actually an accepted theory for a very long period of time prior to John Dalton. We credit him with this because it was one of the first public records we have of the theory of the atom in modern times. So if I had to draw what the cannonball looks like, I would probably draw a sphere. Of course, it's hard to tell that's a sphere. It looks like a circle, so I'm going to put a little shiny spot on it so we know that it is actually three-dimensional and it's solid. The video you're about to watch actually shows the experiment that J.J. Thomson did way back at the end of the 19th century or the 1800s that proved that there was a negative particle in an atom. So go ahead and watch this.
This is the cathode ray tube. Inside, there's nothing inside. It's actually a vacuum tube, so there's nothing but a vacuum on the inside. And it's called the cathode ray tube because this is the anode and this is the cathode. All right. When it's hooked up to an electric current, like I'm about to do here, you can see a beam moving across. You might think it's light, but when you take a magnet to light, does it do this? You can see that it's bending or deflecting away from the magnet, so we know that it's not actually light. What J.J. Thomson summarized was that he was seeing a piece of an atom flying from one end of the cathode ray tube to the other, and that the piece of the atom that he was seeing was negative based on the end of the magnet that was causing a repulsion. So the negative end of the magnet was causing repulsion, therefore the particles must be negative.
So let's try to draw a two-dimensional drawing of what just happened to kind of remember this. There's two experiments. This is one of them that you will have to memorize and understand and be able to answer questions about because they are so significant to the development of the theory of the atom. So what we were looking at was a cathode ray tube. Inside the tube was a vacuum, and when they put electricity across it, you saw a relatively straight beam produced across that tube. And when he put the magnet across it, you actually saw a curve to that beam. And from the fact that it was the negative end of the magnet and the particles moved away from it or were repelled by it, he deduced that it must have been negative particles in that beam. So let's go ahead and record some observations based on this experiment. The observation was that the particles were repelled by the negative end of a magnet. Based on that, he figured that these particles were negative. But overall, we have known for a very long time that an atom has no charge. So if there are negative particles in an atom, there must also be positive particles in order to outweigh those charges and have the total atom be neutral. So there must also be positive charges. I'm going to write particles. All right, so those are the major things you need to walk away with the J.J. Thomson experiment. Now, what he concluded the model must look like now, we actually call the plum pudding model, which I'm guessing in England is a pretty common dessert. I know my in-laws really love bread pudding, so that's what I think of when I think of plum pudding, except that instead of plums, they have raisins in it. But essentially, it's a pudding, and in it there are particles. And in the case of the bread pudding, it would be the raisins in there. But I'm sure you can think of other things, like maybe rice pudding, that you have raisins in, or something else. But anyway, how that would look is, again, a sphere. And this is still a solid sphere. The difference is that in this sphere, we have positive and negative charges. And recall that they have to be the same number of each because they need to total 0 overall charge. This next video that I'm going to show you, the gentleman has a beautiful English accent, which I kind of like for showing this because it is an international work, us discovering our current theory of the atom. But you'll notice partway through that he's using a doorbell in order to indicate the detection of some particles, and that does get a little trying on the nerves. So just work through it and try to listen to what he has to say, because this is the modern version of the experiment that Rutherford did way back at the beginning of the 20th century, I think in about 1909. So really fascinating. And the things that he was able to deduce based on that were amazing. So here we go.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
All right, so let's take our two-dimensional drawing and try to render what was happening in that experiment. So this here is supposed to represent our alpha particle emitting radioisotope, and the particles are going to be directed toward the atoms of the gold foil, which are the gold dots with a small dark nucleus. So most of the particles are going to pass directly through undeflected. So that's what's going to happen to the majority of those alpha particles. The occasional one will actually come in and hit a nucleus and be deflected back. Some, when they come in, will approach close enough to a nucleus that they will be deflected out like this. But again, the majority of them are just going to pass through completely undeflected. So I'm going to label this like the majority because I'm not going to draw that many. And then some, and then very few. And that's what happened in Rutherford's experiment, and you saw the modern version of that today in the video. So the observations that were made based on this example were that most particles passed through, and that some were deflected, either directly back or kind of curved based on the electromagnetic field. Based on these observations, we can actually draw some conclusions. One of those conclusions is that atoms are mostly empty space. That was huge. All through recorded history up until this point, they thought that atoms were small, indivisible spheres. Even after Thomson's experiment, they just thought those negative charges were inside the atom, not that the atom was mostly empty space. They still thought it was a solid sphere. And then the other thing was that those positive charges were not in the sphere overall, but instead were concentrated in a very small place we now call the nucleus. So we're going to say concentrated positive charges. We now call that the nucleus. So based on Rutherford's experiments, he came up with a new model, which we call the nuclear model. In the nuclear model, we have a small, dense, positively charged nucleus, and then the electrons are just outside of that. He didn't say specifically where they were. That's where Niels Bohr comes in. Niels Bohr, based on some experiments, and actually if you haven't done it yet in class, you will do it soon, but based on the different colors of light that are emitted from electrons as they drop from the excited state to the ground state, Niels Bohr concluded that there must be specific amounts of energy that each electron can absorb and release. Therefore, they must be in very specific places. So he said that electrons follow specific paths. We call the model that Niels Bohr describes the planetary model because it is not unlike our own solar system in that you have your central nucleus, but he's saying that the electrons are in specific paths. Ooh, I'm not good at drawing circles. Around the nucleus, like so. Hopefully you can draw concentric circles better than I can. We have since found that that is not true based on the work of Werner and Heisenberg and lots of other scientists over long periods of time, that electrons' position aren't necessarily just based on their energy, which is what Niels Bohr came up with. They're actually in regions of probability. And those regions of probability have different shapes and are at different distances from the nucleus based on the energy that those electrons have. So essentially, what Werner and Heisenberg came up with was that based on the electron's energy, we can draw a region of probability where we can most likely find that electron. Those regions of probability we call orbitals, not orbits, orbitals. They are three-dimensional shapes, not rings or paths around the nucleus like you see in the Bohr model. So we're going to say this is called the, well, let's define this a little bit. Electrons' positions are based on probability. Whoops, I spelled that wrong. So we call this model, there's a couple names for it. We call it the wave mechanical model. Or some people call it the electron cloud. As soon as you try to point to where an electron is and say, hey, there's an electron, it's not there anymore. So we kind of draw the electrons as if they could be almost anywhere. So we're gonna draw in our nucleus like so, but our electrons could be anywhere outside of that, like so. So that's why they call it the electron cloud or the wave mechanical model.